So this is the first video where I will be showing you the usage and application of Tensorscout, which is a Python package that basically a collection, a very lean package, the collection of 4 decorators that were made with the intention of making multiprocessing simpler, of really democratizing the whole process for uh, multiprocessing, right? And multiprocessing is it's as simple as splitting the number of tasks you may have available to compute across separate computers that you may have available somewhere in the cloud or in a server. And so then after you allocate the task to the specific computers, let's say we have 16 tasks and we allocate each task to a separate computer, then they can be run in parallel and they can return all the outputs back to your initial computer. And that way you can save a lot of computing time. The runtime is significantly reduced, of course, in that way, and this is actually very known. These techniques are very known in cloud computing, server computing, of course. Applications that I'm more aware of are in the fields of molecular dynamics, Monte Carlo simulations, but I bet that it goes beyond that even. We may even have find applications in gaming or financial analysis or things like that. An idea that which occurred to me, and of course I'm not a financial advisor of any kind, so I must stress the fact that this is not financial advice. But for instance, an example external to what I was going to show is on batch backtesting, right? And of course, this, as I mentioned, I'm not really. It's not my field of discipline, but it's just some idea which occurred to me, just to kind of like advertise this package, this open source package, of course, that you don't have to pay anything for. That batch backtesting would be something like this. Right? Say you have like a historical database of I don't know, Bitcoin, right? From 2012 all the way to today. And let's say you want to pick all the candles, 500 candles from 2012, right? Then you want to pick other candles from 2021, and then you pick another one here, and different, really in different time windows, right? So after you pick, let's say this specific time window, you want to calculate the rate of return or rate of investment of a strategy that you apply to it, right? Let's say you have 100% ROI there, which is great ROI. 25% here in this space, then you get 35, then you get 50 here, and so on and so forth. You could do this in series with a single processor, but it's easier really to, if you had 4 processors, you could do 1, 2, 3, 4 all at the same time, right? So that would be an application to it. Of course, what we'll be doing here is an application to something a little different, and we will be basically showing you the usage of this method from Tensorscout. And this method, Campfire, really what it does is it decorates a function that returns a dictionary, and that function which returns a dictionary is to be iterated, is to be repeated a n number of times, right? Let's say you want to simulate a political election, for instance, right? And you want to simulate it 100 times, then you can split those 100 different simulations across 16 different computers, or 16 different cute little robots here, right? As in the now this was drawn with DALL-E, so there's no copyright infringement or anything there, right? Yeah, so let's say you wanted to split 100 different simulations from a political election, right? Across 16 computers. You can do that with Campfire, as long as you have the simulation, the output returned as a dictionary. And now the power really behind outputting a dictionary is that you can define really, the sky's the limit with what type of data structure you want to define for each entry of the dictionary. You could define the first one as a string, second one as a list of strings, the third one could be a 4th-dimensional array, and fourth tuple, and so on and so forth. The list is really you have it's a very versatile way of representing returning data. So what Campfire does is you decorate your function um, with a dictionary that outputs a dictionary, and then once you have split them across all the computers, the consolidation then all of the information from all of those separated computers gets consolidated back to a single dictionary. And so that's very useful if you want to, for instance, extract a specific feature from your simulation that has 100 different possibilities. Let's say like the fourth feature is like a percentage of this politician winning, and so on and so forth, right? So there's a lot of power there. And so I will be using, there are some examples. If you want to read over the documentation, just go to tensorscout.readthedocs.io. But what I will be doing something new, of course, for this video, because it's a video and it's not. Otherwise, you just read, the documentation there. So I will be showing you something that I think is a little creative, or at the very least a little bit interesting, which will be random walk in 3 dimensions. Okay. Now, random walk in what is random walk, right? So in 2 dimensions, it would be a sequence of random moves across the 2-dimensional plane. So let's say you can choose only up, down, left, or right for each move, and you start at a point of origin. Then if you pick one of those directions at random, let's say up, then the next block updates to going upwards, and then it iterates from there, whether you choose the next direction at random, right? It's left, so on and so forth. It's as simple as that, really. But what we're going to be doing is we're going to be simulating in 3-dimensional space. So for that, we'll be creating a new file, an empty file. We're just going to call it RW3D for random walk in 3 dimensions. Now we're going to access it if, oh no, not this. Sorry about that. Okay, code random walk, and it's empty. Okay, that was something that I was trying before. Okay, so the first step would be to import a numpy because we'll need it. Okay, now if you think about random walk, of course, what comes to mind for me, at least when you're talking about 3 dimensions, is the 3-dimensional space. We need to declare it. Our 3-dimensional space is we're going to be represented as a sparse 3D matrix or 3D array with a length scale of L. Let's say we wanted the space to be a 20 by 20 by 20 empty cube, then the length scale would be 20. All right. Now the next thing that I think that is probably goes I'll just add it here, is the sequence, the specific direction of all the available moves. Right, so that would be basically up, down, left, right, or top or bottom in 3 dimensions. So that can be represented also by 3 entries for each of those moves. Because we're here using zeta, y, x as the norm in terms of like the directions. We start with zeta, we assume that let's start with bottom, represented by -1, 0, 0. The first one is depth. Okay, so that would be bottom. The second one would be top, only going to the top for that direction. The third one would be going down, which would be in the y-axis, -1 in the y-axis, and everywhere else 0. Up, which would be +1 on the y-axis, everywhere else 0. And then the x and the left and right, of course, now it's become evident to you probably, would be -1 in the x direction and +1 for right. Okay, that's it. Those are the moves. Now, of course, random walks should start at a point of origin, right? So we can start with say we start with a three-dimensional cube in at an origin. Now, where would that origin be, right? I will be choosing the origin to be in the middle of the three-dimensional array. And now for that to work, we'll basically have to choose the coordinates to be at the middle of the length scale for all of the three different dimensions. So that can be achieved by doing floor division of the length scale for all those. So those would be the coordinates of the origin, right? In this case would be 10, 10, and 10 for the middle of that whole empty space. And so after we define the coordinate, we need to update that space within the coordinate that we've chosen. And of course it should be tuple of the coordinate. And we need to update it with instead of a 0, because remember that we are in a sparse array filled with zeros, we're going to update that specific point with a 1, which will basically be symbolizing voxel, a solid voxel. So that would be basically the initialization. This is how we initialize the first point, after which we will be choosing the next trajectory at random, the next paths, the next directions. Okay. So then the next one will be the loop. And for the loop, what we'll be doing is we're going to be choosing one of these moves at random. So for that we need numpy random integer from 1 to 7, because it's 7 exclusive, 1 inclusive. And then we're going to be choosing only one point here, and then just because of the syntax of random integer, we need to choose that first entry, which would be really any number from 1 to 6. Okay, so that would be, and we're define this number as the move index, or move IDX for short. Now, to update the next iteration after the initialization, we basically take moves, move index, and whichever number, let's say that we pick 3 at random, then by doing this, we are assigning the key to the dictionary, then it will extract 3. Would extract these values. And I should probably not define these as tuples, but rather as lists, and I'll explain a little later why I did that. How do you do this? Yeah. Okay. All right. And of course, we update the moves by the move index, right? So that would be, let's say it was 4, right? Then it would be, this would output 0, 1, and the list of 0, 1, and 0. Now, of course, to that list, we need to update that iteration now with space tuple moves. Actually, I'm wrong. Sorry about that. This would be, I'll just redefine these moves as that direction chosen, right? Chosen direction. And now to update to the specific space that we've moved from the previous step, what we will do is we go coordinate. We'll need to add over all the entries. So basically, if we start at coordinate 10, 10, 10, and we choose key number 4, then would be 10, 11, 10. Right? For that, we will just update the coordinate in this way, because we are actually updating them from a list. Right? So we are not using numpy arrays here. So we do it this way for I in range of 3 for all the 3 dimensions. So that's the updated coordinate. And this we can call update. Okay. And so then, after this update of the coordinate is done, then we repeat again. We populate that newly updated coordinate with a value of 1. And that's looped over as many iterations as you would like. Now, of course, I'm not going to do a for loop here because I'm going to have to use a try except constraint, and I'll explain in a little bit what that is. Right. So what I'll do in to begin with really is I am going to define all of this inside a function. Okay. I'm going to make this a little larger. This is going to be make paths. Okay. And so the initial value will be just the length scale of the space, three-dimensional space. Okay. And the second one will be the number of epochs or iterations. Let's give it a predetermined value at 100. Now, of course, it will not be iterations in the way that you think, so I'm not going to be using a for loop. I'm going to use a while loop while number of epochs is greater than 0. And now this is how we're going to have it work, really. This, before the for loop, before the while loop, is just initializing the origin. But after this is where we do the update. And so the update here will have a try except condition. Okay. And the try except condition will come here. Try direction. And the reason why we need this try except is because let's say we end up with a coordinate that has an entry larger than one of the dimensions of this three-dimensional space, then it will pop out as an error. So that's why we need this condition. So if there's no error really, everything's fine, and we reduce the number of epochs by one unit. Otherwise, nothing happens. We could write out of dimensions. Try again. Try again. Okay? And that's it. Then we can return the space. Not space, space. We can return the space, and we could just define, we can just create an A array, make paths, and just keep the predetermined values as they were. And that should give us what we're looking for. So we can use the command line here to run it, see what we get. I'm actually going to print the space, the populated space. And let's actually make it, let's make it like a little smaller, okay? Let's make it a three-dimensional space of 5 units in length scale, and just 10 iterations. Alright, and let's just print it, see what we get. Yeah. Okay, so you see that this worked, right? That we have point of origin, and then it for every iteration it just adds an additional solid item within the three-dimensional array. Now, of course, as I mentioned, well, I didn't mention this, but it would be nicer if we have a three-dimensional visualization. And so for that, we're going to be using VoxelMap, which is another Python package that I created for three-dimensional visualization with arrays. For that, you need to create a virtual environment to install all of these packages. That can be done by virtualenv, or just just finding your own way to do virtual environment. And so you click that, it will create a virtual environment. I've already created that one, so I don't need to type that and enter. So I'll just access it. I created my virtual environment in the desktop, so wherever you find your virtual environment, you just need to go there and then source activate it with this command line. So now you can see that I have the VM suffix, which is the name that I attributed to my virtual environment. Now in that virtual environment, you install VoxelMap. And then after installing it, you can import it. So we'll import it here. Import VoxelMap as PXM. Okay. And now VoxelMap is very easy to use. You could just declare a model object with the model class from VoxelMap, and it incorporates the data as an array. And then we could use this draw method to draw the array which was made. Okay, and so we run this. Again, we run the Python script, and then we should get a graph now. Now it's a very simple one. You know, it looks like a three-dimensional structure because it is. Each point is actually a part of the trajectory, right? So if you don't know where that initial cube is, you could color code it. That's something that VoxelMap can do. So VoxelMap has this really interesting feature which I made, where we can assign a color and transparency to a specific number in that three-dimensional sparse array. So let's say I wanted to just attribute the first point will have a value of 100. Okay. Then VoxelMap has this variable which is called hash blocks, which is particular really to the object that we've defined, where we can define the color and transparencies of those numbers that we have in the array. So the first one, let's say we want to make it cyan. And of course it needs a transparency. We'll add the transparency of 0. The other ones, as I've shown, are just the values are 1, a value of 1. So 1, I'll just make it white, and a transparency of, let's say, 75%, or opaqueness of 75%. And now I'll draw it. Now, of course, for this to work with this color key, so to speak, we need to change the coloring method to custom. And I'll just make the background also. I'll change the background color to black because it's nicer. You can change it to black. And if you'd like, now we have also a new feature for VoxelMap, which is called geometry. And so you can choose between either voxels or spheres. I believe spheres are called, what did I end up calling spheres? Let me see. You need to go to the, I need to go to the VoxelMap documentation because I don't remember. So I'll just do this. How do I do this? No. Cool. I think it's probably faster if I do this. Okay. Need to go to the documentation, to the API reference, local methods, and geometries. Geometry is under draw. There. Yeah. So you see, geometry is set to voxels, but the other geometry available is particles. So we can change it to particles. I think it may be nicer that way. And now we can rerun the algorithm. So you see that we started at the cyan, that's the point of origin, and then we went with a random walk to different spaces, to different direction. We may have gone up, down, etc. Now we don't know exactly which of these directions those additional spheres pertain to, but we can easily code them, color code them with VoxelMap as well. So instead of, for instance, instead of attributing a number 1 to the updated space, to the updated solid, what we can do is we can attribute the key of the moves, right? And in that way, they will represent the direction that each of these are taking as the trajectory evolves. So for that we can change that. It's as easy as just changing it to move index, right? And these keys are the move indices. Now of course we would need also to update the color here, right? The color, to color code it, we need to declare it in the hash blocks variable that pertains to the VoxelMap model. Okay, so we'll just define them red, white. Let me just copy this several times. Red, white, blue, magenta. Now we're doing CMYK now. Yellow, and we're not going to do black because the background is black. So orange. Now we're going to redraw it, and you should see that now the draws are pertain more to. When I cancel that out because it's becoming annoying. The printing out of dimensions. Okay. And now you see that we started, right, with the origin, which is solid color. The other ones are faded because I changed the opaqueness to 25%. So it started, and then it seems that it's gone to the yellow. And yellow, what does yellow pertain to? Yellow is number 5, and here number 5 is going to the left, right? So the correct orientation is really like this. If you would like to be more specific, right, the color can help a lot. The orientation is this, goes to the left, and then it reorients itself, and it goes to the left, right? And so these are some really interesting, it's a very interesting thing that you can do really to represent your models in that way. And VoxelMap is really great for doing this visualization because it uses the BTK library. It just really optimizes visualization and three-dimensional rendering. You could even make your labyrinth or three-dimensional random walk more complex even. Instead of 5, you could increase the space to 200, to a three-dimensional isolated space of 200 with a length scale of 200, and you could have it iterate 1000 times, and then create a large random walk chain. Hopefully it won't take long. Won't take too long, hopefully. Yeah, you see? So now it created that random walk chain. It starts, where does it start? It starts at the cyan solid particle, and then it just goes on from there. And it looks a little bit like a polymer, right? If you're familiar with biology or whatever, right? So it's kind of cool. You could do the random walk again, and it will give you a different structure or path, so to speak. Right? It looks like a chain, even like a necklace or rosary or something. I don't know. In here, I'm having a little bit of trouble like identifying the point of origin right now. It's making me a little loopy. It's probably somewhere here, where it's because if I made it more transparent, I will find it easier. But because it's not so transparent, it might have been, or it's probably here in the more dense place of the path, three-dimensional path. Okay. Now, of course, for VoxelMap, you also have kind of like showcase advertising it a little bit. You also have the voxels option, which is a default, which will just do this visualization with cubes, right? So for that, you change the geometry to voxels, and it does it, right? It's just boxes now. Okay, so now you were probably, I'm not sure if you're already growing a little frustrated, but probably thinking, oh, how can I apply Tensorscout, that multi-processing library to this, right? It's as simple actually as importing the module. For that, we will be installing Tensorscout by typing pip install and then followed by Tensorscout. Scout. and just like that, installs it pretty fast, faster than VoxelMap even. Okay, so what we'll be doing here is, instead of just simulating a one trajectory individually as we have been doing, we are going to be simulating 4 trajectories at the same time. Okay, and so for that we'll need to import Tensorscout, as I mentioned, and let's just import it as Scout to make it shorter. And so the decorator is called Campfire, so it's going to have to be called with scout.campfire. Now, Campfire is composed of has two inputs to pick. The first one is the number of iterations, which is called num_inters, I believe. And so we'll just choose 4 iterations, as I mentioned, and we're going to split across the 4 different cores or CPUs that my computer has. So it's as simple as that. Now, this function is decorated with Campfire, and it should work to do exactly that. Okay. Now, of course, Campfire requires that your output should be a dictionary. So instead of returning space, we're going to return a dictionary, and we could return the space, sure, but it's going to be a lot of memory. Well, I'll just do it. Space, space. Okay, as simple as that. And hopefully it can handle it. Though I'm skeptical that it would, because it's a lot of memory. But let's just try it like this. Okay. And so now makePaths is now decorated to handle. Of course, this has to be enclosed. That variable has to be enclosed in brackets for it to work. So this is so that they can be the tensors can be divided as separate entities. Okay. So now paths, instead of this, I am going to change it to a dictionary, dict. Okay. And so now I'm just gonna have that's gonna create 4 different simulations at the same time. Okay. So this is what's gonna happen now. I'm gonna change this. I'm just gonna uncomment everything, right? And I'm gonna run this now. So again, we're gonna run this again. And it didn't return anything because we didn't output anything. So we could print the first value of the dictionary, right? Print dictionary space. And it's actually gonna print, if I do just this, it's gonna print the four different simulations, the 4 different tensors that I created. So I could, like, for instance, instead of doing that, just print the second experiment, which is indexed by 1. So I do that, and it's going to print that large array. Now that large array by itself is nothing, right? So what we can do is we can just like model it here with that. And we can make this into a separate function as well to just make things faster. I'm just going to create a definition here, or a function, def make model, okay? And then it's going to take an array. And then that array is going to be this thing. I'm going to take that. It's going to take that as an output. Okay? And now, so basically what it's going to do, what's going to happen here, we could just bring all of these things downwards. No, not all of these, sorry. Just these. Okay, and now we can run the simulation again, right? This dictionary is going to create 4 different simulations. So what we're going to do is I'm going to call make model. And we can even like make that into a for loop if you'd like, right? Okay, and there will be for I in range of 4 because it's 4 different simulations that will already run simultaneously. So it's as easy as that, and that will draw the 4th. It will run all those 3-dimensional random walks at the same time with the 4 processors that I have, and then after that it's just gonna plot the 4 different paths that were made. Okay, so for that, after that we've made those changes, we can just call the method, the script again, and it will do that, right? So you can see the results. It didn't give me anything for some reason. I'm not so sure why. Why did it not do anything here? Make model space. I need to do some troubleshooting here. Let's see. Some troubleshooting. Why? And I just want to see that I'm getting the right thing. Sorry. Let's see. So yeah, it's 200 by 200 by 200. So why is that not working then? Aha. Okay. Let's see if this works. Yeah, that works. Right. Okay, so there's something very strange, and this is something that I may need to correct, or maybe it's just a feature, so to speak. But the thing is that VoxelMap can only take one variable, and then you have to define another constructor object for it. So that's a little bit inconvenient, right? Because let's say we repeat this, and we repeat it twice, it's not gonna give me two plots. I mean, it's not gonna give me two different renderings. It's gonna be confused by the second rendering that I do. Right, so the first one is this. Okay. And the second one, oh, it did work. Okay, so for some reason the for loop, it's having problems with the for loop. That's a little weird. But so I'll just show you really quick. Okay, I'll just copy paste this, and then maybe I can work out the bugs for VoxelMap if it has any. But yeah, so in this way, you can just run. This is a good example of how you can run 4 different simulations, split them across 4 different CPUs so they run simultaneously. And then after that, the plotting is just the fastest part, right? So you have this plot, the first simulation, right? Then it's drawing. The only process here is just the drawing. That's what's making it longer, because the calculations have already been done, right? So that's the second one, then the third one, and there's only 4, but you can of course you can choose more if you'd like, right? So fourth, and sorry, third, right, and fourth. And of course you can add more variables here. Let's say just, yeah, that's the fourth plot, right? And you can see that there's highly complex trajectories. You can go close in, zoom out. So I really like VoxelMap. I think it's a great package to use as well. All right, but yeah, you can add like more entries to your dictionary. Let's say make it a little bit more complex here, and we can add space. We can add, maybe we just want to return all the trajectories that went to the left. We can add a left variable, append coordinate if it went to the left. And what would be left would be if the fifth direction, right? So it's zeta xy. So if what was it? Sorry, move idx. If move index is 5, then you append that coordinate. Otherwise, you don't. Okay, and of course you need to define it here as well. Lefts, and it starts with an empty list, and then you kind of define it as part of the dictionary. Lefts, you can add it here, and of course you need to enclose that with the brackets so that they can identify, so that Tensorscout can identify each simulation as a separate entity. And then we can even like a test variable, right? And a test variable, we could just give it a value of 1. Okay, so in theory we should get 4 values of 1. But let's say we want to like change the number of iterations to 16 and I split them across 4 different CPUs that I have. Your computer may also have 4 CPUs because that's usually the more modern computers, they have at least 4 CPUs or more. So we can have it return all of these variables also. So for that, we run the same dictionary, and let's just like uncomment these out. And we can now run, and then after running all of these, we can reference to the left variable, and we can just let's say we want to pick the 8th simulation that was done. We can print a value for that. So L8, I'll call it, and then we print L8, the variable, and then it should give us the left coordinate information for the 8th simulation. So we run it again, and now that's what we get. We'll get a list of different trajectories from the origin all the way to the last iteration, the last 1000th iteration. For some reason, it's giving me a mistake. That's because, as I mentioned, all of these variables need to be enclosed by brackets. Okay, so I forgot that. Don't forget that. We run it again, and now we should get a list of left trajectories for the 8th simulation. And of course, it takes a little bit longer because now it's 16 different simulations. But yeah, so now that's what we obtain. You see, it started, of course, at the origin, and the first left was in this specific coordinate in the 3-dimensional space, then the second left, and so on and so forth. Now, if you wanted to really test and be sure that it's running, it's making 16 simulations, you could instead print. We could also print the, what do you call it? Dictionary test variable, right? Test var. And so that will print 16 entries of 1. We'll just print that. And of course, when you split your tasks across 4 cores, and if it will work in parallel, it will reduce the time at least by 4. Unless well, not at least by 4, but it will reduce the time significantly. So you can see now there's 16 entries, 4, 4, 8, 12, 16. So that's basically a very high-level application or overview of how you can use Tensorscout Campfire specifically to, just divide your simulations or divide your calculations and output really complex data. So that would be it. As I mentioned also, I used VoxelMap as a library so that we can do the visualization, but I guess like that's the gist of it. Thank you for watching, and I hope you find the video helpful or interesting or cool. If anything, just subscribe to my channel if you like what you're seeing. Thanks. Bye.